Hello, everybody. Ooh, that was louder. Is your 3D printing stuck in a rut? Do you think of printing the same 3D printed plastic Yoda heads over and over again? Today's Fireside Chat is going to help you get out of that situation. We're going to feature a friendly conversation, a fireside chat between Allie Katz and S.J. Jones. Allie is an inventor and product designer and does a lot of interesting, non-traditional 3D designs, kind of pushing the boundaries of what you think of as traditional 3D printing. SJ, on the other hand, is a design engineer in metal additive fabrication and has worked on things as diverse as custom prosthetics and aerospace parts. So this is going to be a talk about an edge of 3D, a corner of 3D printing that you don't hear often enough about. So please join me in welcoming to the stage Allie Katz and S.J. Jones. Mike is hot.
Thank you, Elliot. I like that this started sounding a little like an infomercial, so I kind of feel like we're going to continue like that. So I hope y'all are ready to get your wallets out. We are going to be selling the hottest metal additive technology on stage today, and you will all be the first buyers of it. I am actually very much taking the piss right now. I am Allie Katz. It's really nice to see y'all again, SuperCon. You've maybe seen me before on the stage wasting your time, but you know, they keep inviting me back, so I'm really sorry you have to listen to me talk again. But this here with me, this is S.J. Jones, the real star of the show today, our absolute best possible expert in metal additive. And yeah, we are gonna talk about all sorts of 3D printing today because between the two of us, I think we cover, it's a significant chunk. Elliot said a corner, but I think we cover probably 3 corners, like collectively.
Just 3?
You know, I'm willing to admit that, you know, we're not maybe going to talk a ton about SLS nylon today, you know, like there's a few technologies that we might not really touch on. So I'll let someone else have a little bit of 3D printing to keep. But we're taking the rest of it and nobody can stop us. So for those of you who aren't already familiar with me, as Elliot said, I am an inventor, I am a designer, I'm an artist, and I'm obsessed with 3D printing. I've been doing it for several years. I am self-taught, which is fun. And I have spent a lot of time kind of in the polymer, you know, your plastics, your FDM and your SLA and stuff, that side of the universe. And I'm actually wearing my latest project today, which is entirely made possible with 3D printing. I was gonna say, actually, would you like to hit the button on the back? There's a button on the top. This has many, many switches and buttons. And then I will also
There's something red blinking.
Perfect, that's what we want.
Okay.
And then we're gonna flip a switch, and then we're gonna wait a second, and it's gonna freak all y'all out because it takes a second. It's not
All great
instant.
things do.
There we go. So this is, that's, of course, deciding to be a little sleepy now. But it's basically, it's solid sterling silver, but it was done with 3D printed wax resin. The leaf is an elastic resin. The gears are 3D printed. Everything in this is somehow related to 3D printing. It has a thermal camera in it, which is why it's now being nice and relaxed, but if I hold my hand in front of it, it wakes up. But we're gonna leave it on and just see what happens. So that's my background. Oh yeah, see, it's definitely gonna be a little weird if I hold my hand in front of it, so maybe we will turn it on. Just, you know, to be on the safe side. Now, that's me, SJ. Would you care to introduce yourself a little bit more fully, you know, and tell us a little bit about your background?
Sure. Before I get started, how many people in the audience have an aerospace background? Like you've made planes or anything? Fantastic. Beautiful. So I don't have to explain as much. And then how many of you have a manufacturing background? Even more hands. Lovely.
That's a lot, actually.
Yeah, that's what I love about being in LA, because like there's so much supply chain here, and I'm like, West Coast, best coast for coffee and for manufacturing. But that's all I'll give you. I think I have a really great photo for this intro one.
Yeah, go for it. Yeah, we have a few photos that SJ has been kind enough to share. So there will be some jumping up and down. No, how do we get on the computer? Oh no, technical assistance, por favor. Don't worry, we'll get there eventually. It's fine. Huzzah, huzzah. Yes, introduction photo. Huzzah, yeah.
Oh wow, that color,
wow,
that
that-
color change. I'm not blue, but you know.
That's fresh. I don't know what's happening there.
I don't know what's happening there.
We're gonna leave that one also up to technical people to figure
it's
out.
art. Honestly,
Yeah.
there's a filter on it. We'll call it art.
Yep.
It's a Banksy or something. But yeah, so I started in metal 3D printing like 2018.
Some years ago.
Many odd years ago. So I'm a biomedical engineer by education and training, and I got into 3D printing because I wanted to 3D print devices to help make the world a better place and to save lives and to make a difference. And so when the pandemic came around, I was like, my moment, it's here. But every hospital that I called and contacted during the pandemic, trying to like work with them, collab with them, get a job with them, they did not want to pay an engineer's salary. They said, we can teach a nurse to control P rather than hire an engineer. That seems really expensive. And so I really still wanted to be in 3D printing no matter what it was, because I knew that was like my passion. And I was literally cold calling a bunch of companies and was just like, hey, I'm writing a blog. Can I interview you real quick? And then I called one company and interviewed with them, and they were making aerospace parts. And then I was like, oh crap, I forgot to ask if they were hiring. That was like my final tagline, is I would like end the little interview calls. And
That's genius, by the way. That's very smart.
the hustle was real, okay? The hustle was real. And so he called me back literally the following Monday and was like, hey, we got off that call. I forgot to ask, are you looking for a job? And I was like, yes, thank you, I absolutely am. So that company was hoping that they were gonna be 3D printing patient-specific implants, the talus specifically, out of cobalt chrome and titanium. So like you break your heel essentially, and then we need to print you a new one and then just click it back in there.
That actually sounds remarkably simple. I'm sure it's not at all, but I love the way you made it sound. And I say this as somebody who actually has metal parts in their body, which was a traumatic experience of having to get. But yeah, that sounds nice. It doesn't sound horrible at all.
Oh yeah, no, the horrible part was cleaning the STLs. It was not even printing the parts. Getting a clean STL, that was the hard part. And so yeah, I was actually printing those in this machine here. This is the EOS M280. How many of you all have a Prusa machine at home? This is the equivalent for metal 3D printing. The EOS M280 was a beautiful machine. It was a beautiful era. These have now phased out. We no longer have these, but everybody is currently on the black market trying to buy them at auction if they can. They no longer make the parts for this one, so people are just like buying them to get the parts.
What's the running price for one of these aftermarket?
Not
Just so
that
people
much.
can start saving.
Oh,
you know?
yeah. Well, if you did want to start saving, for this particular version that's discontinued, probably around like, you can get a good one for like 80K.
It's a bargain, guys.
A bargain. It's a steal. Its replacement is the EOS M290. That one's running a couple $100,000.
That's still like a small price to pay for what I'm sure is a significant upgrade. But if you wait until later in the show, we'll be offering a significant discount on that price. So stay tuned. You gotta stick around. But please do continue.
So I joined that company, and you guys are in California, so you're very familiar with like the whole like merger and acquisition cycle that hits certain industries where like all of a sudden everybody's buying everybody. So I was there for all of 3 months, and then we were acquired by a rocket space company called Aerojet. Yeah,
Sounds
they're
like
here.
there's some people who are familiar here, perhaps.
Yeah, again, they bought us for a really good deal. Also, only a couple million.
Discounted price.
And so, they bought us for a couple million, and then all of a sudden they were like, Aerojet came to us and they said that they have insurance for like rocket pads and rocket launches, but they don't have insurance for if one of the implants fails. So we're gonna have to kill the medical portion of our business. But if you'd like to stay on, we'd love to have you. And so that's how I pivoted from like the medical industry into the aerospace industry.
They were like, surely you know how to make medical devices, so rocket parts. Like that's like the same thing, right?
Yeah, basically that's what they were. It all prints on the printer. It's the same. And I was like, all right, I guess I don't really have a choice because have you seen my student debt?
Ooh, yeah, that's a mood. That is definitely a mood. But yeah, okay. So that gives us, I think, a pretty good idea of kind of how you came into this and where you're kind of coming from a bit. But again, you are a metal 3D printing expert, like not just like because this is metal, but it was made from wax and then just cast. Like this isn't 3D printed metal. You do 3D printed metal, which is a very, very different thing. And so like as said expert, like how does metal additive fit into manufacturing for space? Like obviously not everything is being 3D printed for our spacecraft yet. Give it time, perhaps. But yeah, you are the source here. So like talk to us a little bit about how metal fits into space manufacturing.
Trying to figure out how to answer this
Sigh.
delicately. So essentially, like a lot of the space manufacturing that I have done is when you're going to space, you're experiencing some of the hardest conditions that you've ever experienced. The weather up there, I wouldn't even call it weather. It's just everything's trying to kill you. Everything's trying to knock you out of the sky. And so you need to have materials that are very specific to those conditions. And oftentimes we don't have a conventional way of manufacturing very rare metals that can survive in like the climate of space. We need things to be super lightweight. And sometimes when you're making something conventionally, lightweight only goes, we've really pushed the envelope on that pretty much as far as we can go. So using 3D printing, we can make super lightweight components. We have access to more materials. And also, the kicker is that people assume that we can get it faster.
But surely you can, right?
I mean, technically, yes, I can print the part, but getting the part qualified and getting the part approved, like by the bodies that be, to go to space is a lot harder. I would say that like
Harder than traditional manufacturing processes?
much harder than traditional.
Okay.
Well, I mean, we've been doing casting for like hundreds of years. So like, if I bring a casting and I'm like, yeah, this casting, it's got like a 1-inch hole in the bottom right quadrant. They're like, all right, that's fine. Put it on the ship. And then I'm like, yeah, so my 3D printed part, there's like a 60 micron bubble. And they're like, ooh, I don't know. I'm gonna need you to print a whole lot of tensile bars to prove to me that it's not gonna break.
Rude.
Yes, exactly. So the deal is not really there, but it does solve like certain design challenges. It solves a lot of supply chain problems, and it potentially could solve future supply chain problems. Elon seems to have figured it out with the rate that he is like getting those rockets up there and back.
Do you know that he is 3D printing those rockets?
Oh yeah.
Okay.
Oh yeah, they're definitely 3D
I
printing
trust you.
rockets. That's the only way that they can hit the performance, and then also like he does it all in house. So like when you do choose to go the metal 3D printing route, you can bring a lot more manufacturing in house, and that's also where we see that like metal 3D printing fits in really well. You have a lot more control over the manufacturing, the design, where it's made, how it's made. You have access to all of like the build files, the temperature, the thermals. You get more data than you want, and also it creates just more headaches for the metal additive engineers because it's like, I have to submit how much metadata before you'll approve this? Casting doesn't, forging doesn't, but okay, if that's what makes you feel better.
It just means that you know so much more about this than everyone else.
Like, the more you know.
You know, you mentioned rare materials. Like obviously there's conventional materials again that we're aware of for kind of these sort of things, but what sort of materials are you getting to work with when it comes to 3D printing metal parts?
So my favorite rare material is called tantalum, and I like it because it sounds like Channing Tatum. But it has like really great applications for like extreme thermal environments. So I've seen a lot of like space thrusters that are like maybe this big. It's like a tiny little thruster, and it's made out of tantalum, and it sits on like the satellite, and all it does is go psh, psh, and it just helps control the satellite while it's in space. I think those are just like, I think that's just like one of the coolest, craziest
really
things.
cool.
They also are using it for like deep sea applications because it can survive like some of the most extreme environments, like deep down underneath the ocean. So I think that like that's a pretty great application.
Is this a natural material,
It
or is this
not.
man-made?
It's man-made.
Oh,
yeah.
that's cool.
Which means it's like really expensive. I held like
sure.
1 kilogram of it, and then I almost dropped it in the container at the conference, and they like 4 booth people like dove at the ground. And I was like, okay, how much is this? For like perspective, like aluminum, like a kilogram of aluminum is like $15. So I was like, how much is this? And they're like, that 1 kilogram that you're holding in your hand is like $1,012. And I was like, oh, for 1 kilogram. And then to fill a machine that's about that size, you need about 30 kilograms. And so I was like, so just to put enough material to print something is gonna cost $30,000. That's before turning the lasers on and melting all of the metal and doing all of the heat treatment processes. And I was like, I don't think I want this.
Sounds stressful.
It's quite stressful. I'm like, And then if the print fails, as you know.
God help you at that point.
God, yes.
No, is this? This is me being curious. I'm not gonna lie. This is not a planned question. I want to know. Is this the most expensive material you've dealt with? Or is there more expensive? Is there more exotic? I know there's one material you've told me about before that was a material that you thought was really cool. Cool enough to name your online name after it for a period of time.
Yes,
Inconel. Inconel. Is that
Inconel super alloy.
Is that
one,
more or less expensive
Oh,
than
significantly
tantalum?
less. Significantly less.
Never mind.
Inconel
I
is
got
less than
excited.
$100 a kilogram.
Ah, that's
Yeah.
nothing.
Yeah,
That's
yeah, so that's not too bad. But I love Inconel. It's a really great nickel super alloy. And so for those of you who are familiar with like traditional manufacturing, like steel, like manufactured steel, if we were to machine a piece of steel and then we were to like 3D print Inconel to like a near net shape and then machine it, we would get like more strength, better material properties, and the cost differential is like almost negligible. In comparison. And then Inconel 718 we're seeing has like a big rise. She's having her moment right now. I love to see it, but it has like an anti-corrosive agent to it. And so with like all of this boom in US manufacturing, like we're really seeing like the drive for more naval applications. So like the little propellers on the back of boats and whatnot, they rust pretty quickly. But if you make it or you 3D print it out of Inconel, then they're like you get a longer life out of the part.
I'm seriously, I feel like I'm very rapidly learning so many more uses for this stuff than I think even I knew, and I knew more than the average bear coming in. So I'm very impressed by this. It sounds like things are continuing to develop in a nice way, which is good for you, good for the industry. What are you most excited about for this industry, for the metal additive manufacturing and the processes involved?
I'm excited for spare parts replacement, obviously. If you guys don't know, there's like fleets of retired vehicles in certain parts of the country where like there's like railroad graveyards, there's ship graveyards, there's airplane graveyards, and like currently because of the way that the process approval is set, we kind of have to go into the graveyard and then harvest the parts out and then ship them out to the field where they're needed. There's a lot of initiative around like 3D printing those parts instead. And then getting those parts out to the field for airplanes, for spacecraft, for tanks, for naval vessels, for things like that. And so like I'm excited for that. And then the other thing that I'm really big on right now is computational design, because we're able to like 3D print these really complex structures almost for free. In terms of like you increase the complexity, but you don't increase cost on the manufacturing side. So that's what I mean by free.
I want to know more about the computational design. Like, tell me, or tell us, I'm not alone here. Tell us a little bit more about, like, when you say computational design, what do you mean? Like, what does that look like? Do you have examples?
Yes, we will have a couple of examples.
Okay.
Let me see if I can.
Because like obviously computational design, I feel like is it's a general term. It can mean a lot of things depending on its use case and what you're doing with it. So I think examples of what you mean when you're talking about computational design would be great. These are some great photos, though.
Oh, thanks. This one's probably like one of my favorite computational design examples. Oh, wow. I love being blue. Honestly.
What's going on with the colors, guys? This is You're definitely like, what is it, like a Dr. Seuss character here.
That's fine. So it's art. At this point, it's part of the presentation. It's art now. So after I worked at that space company, I was miserable having to do all of the qualification work and process engineering. And so I wanted a different job. So I got another job working at Siemens Energy, which was working in oil and gas.
I don't know, dude. Has anyone here ever heard of Siemens? I don't know. It feels like it might be something new for people here.
And so the beauty with oil and gas is that they use very similar geometries. You're making a jet engine plane, except it's on its side on the ground, so it doesn't have to fly, which means that the qualification is so much easier. The materials you can use, they're not worried about titanium or aluminum or the really brittle materials that like to break and fail in the printer. They want the heavy stuff. They want steels. And so it's really just, in terms of like design and qualification, worlds easier. But I digress. So they had this Smart Chopper project that we did, I think it was 2021. It was during the pandemic, where they wanted to make this all-electric motorcycle. So they had this motorcycle that was laying around, and they were like, hey, can you make it all electric? And so they asked us to design some parts for it. And so my first experience with computational design, like printing it and putting it into service, was with this motorcycle. So they really were like, do you think you could make some really cool handles? And I was like, okay. And I was like, what about like foot pegs? And they're like, yeah, give us some of those too. Whatever you can get, put them together. And so I designed these handles and everything. I wrapped some cool lattice around the outside and everything like that. And I find that when I'm like working with new companies or companies that haven't worked with 3D printing a lot, giving them something really pretty first, they really like that. That's where the selling point is.
Everyone likes something a little bit pretty.
Yeah,
Let's be
so
honest.
it's a non-critical component. It's super lightweight. The overall project was pretty happy with it. Oh, we're getting more colors.
I think it's a work in progress. Oh no.
It's not gonna fix.
We're giving up.
I apologize. But if you could see it, there's like a really cool lattice that's wrapped around it. And with the lattices like that wrapped around it, doing like aesthetic changes is like really easy to get qualified. And we can use these aesthetic changes for a lot of other purposes. So you can vary the lattice so that the surface roughness is like rougher, so you get a better grip, whoever's like riding the motorcycle, or who's like grabbing the motorcycle. You can conform the field of the lattice to be like grippy. And we've never had, like, you couldn't CNC that or conventionally manufacture that. And so that's where, like, a lot of, like, computational design comes into handy.
I do find it interesting that that concept does translate over into the wildly less technical but still secretly complex world of, like, FDM 3D printing and stuff like this. Because, like, who here has used fuzzy skin on a print? Yeah, this is the slicer doing a little bit of computational design to create a texture on your print that was not part of the original design. This is obviously wildly simplified compared to what you're talking about, but it's the same end goal, effectively, to create a texture, to create something that can enhance grip without you necessarily having to hand design and hand choose every part of that. Like, admittedly, as somebody who has a fine art background and is used to doing everything by hand, like, the idea of being able to computationally design things sounds really exciting, because it's exhausting to do everything by hand and to not have, like, to let the computer do some of the design, but also
AI. Sorry, you gotta plug it for the disc. You gotta plug the AI so we can get our millions.
Yeah, no, there we go. Sorry, I forgot. We're legally obligated to say the word AI at least once, for any purpose at all. But no, like, this sort of computational design stuff it does show up in other things, but it's so much more complex in metal additive. And I know I'm curious, and I imagine people here are curious as well. So, like, again, I use primarily Fusion 360 to design my pieces. I imagine a lot of people here do as well. But you don't. You use fancy pants software. What do you use?
Fancy pants software. I am a big fan of Entopology. Are there any Entopology fans in the audience? None? Yeah. Heck yeah! Those are my people.
Thank you.
But like, going back to like what you asked about, like what makes computational design different. So like, for aerospace structures, like building an airplane is not easy. Like you have to figure out how the wings are gonna sit, how big is the fuselage gonna be, what's the tail gonna look like, what angle are the Alarians at, what's the nose shape going to be, what radar system are you gonna put inside of it. It's a really big and complex project, but theoretically, like what if you could parametrize that entire design? Right now, we've just been kind of doing like file save as since like the 1980s. It's like the supply chain is so delicate. We can't really do these like big overhauls on how airplanes are designed. It's super expensive. And then the supply chain move, just even thinking about that headache, I'm like, no, we'll make airplanes exactly like this for the next 500 years. It's too much. It's too much of a lift. We're talking global supply chains that would have to pivot to support that kind of a shift. However, if you could do some kind of computational design so that you tell the computer like, hey, these are the things that I care about. These are my design requirements. It's got to go like 500 miles per hour. I'd like it to be as big as this room and as long as from here to that park. And show me some designs. And then here are like the form factors, the material restraints, and the computer could solve and show you a whole bunch of like different options. That's essentially what computational design is. So we're basically parametrizing a lot of our designs and then seeing what the computer spits out. You can then also like plugging our AI. Oh, I'm gonna plug ML.
Oh,
you know, you
okay.
can plug a
Yes,
large
yes.
language model in there.
There we go. There we go. We're ticking all the boxes now.
But you can essentially take those as well. And then you can, if you have simulation work, so like in F1, they have to submit a whole bunch of simulations, and that's Formula One. So like for race cars and whatnot, you have to submit like how fast is your engine, how hot is your engine, all of that like thermal design stuff.
I do feel like anything you're putting a human inside
You need some simulation.
should maybe have
yeah.
some rather rigorous
engineering
testing
work.
on.
So
Yeah.
you save that rigorous engineering work, all those simulations, and all their various designs, their inputs and their outputs, and then you feed it to the AI and the ML, then you let it calculate, and then you give it the constraints and the bounding conditions, and that's how we use computational design to create like new products. That's what I'm most excited, because there's a reason we've been doing file save as for like the last like 30, 40 years. And it's because manufacturing, we've kind of hit the limit of like how far we can push it conventionally. And so with metal 3D printing, we have this like whole untapped design space that we can now bring into fruition. And that's what gets me excited. I think we have photos for that too, if you want to.
Do you have photos?
I mean,
Do it.
will they be in color?
Who knows? We don't know what color. They'll be in some color. Just is gonna be a very artistic rendition of it, but it's fine. I think everyone understands that this is, you know, this is pretty. Oh, interesting.
I have to put it where?
This side. Slightly out of focus, yeah. Ooh, yeah, there we go.
Oh, there we go. Okay,
Beautiful,
thank you.
Beautiful. So, we only have a few minutes left.
Got it.
But I'm trying to decide, like, I want to ask, like, if there's anything that you feel like is holding the technology back, but I also want to, like, ask about, like, the place, like, I'm always really interested in, like, the intersection of art and technology. Like this obviously is something that drives me, and I'm very passionate about. And I'm curious to know, like, does art have any place in the design of functional metal parts like this? Like, is there a place for me?
There is absolutely and always will be a place for you. I'll keep your seat right next to mine at the table. So yes, the biggest place where art fits into metal 3D printing is that when I speak to my machine, these two questions are actually really tied together. When I speak to my machinist, so we print the part in like a near net shape, and then the machinist has to go in and then machine it to very specific tolerances, especially for space applications. However, if I bring my machinist anything that is not a square, a rectangle, a triangle, or any kind of basic prism, he's gonna turn and run the other way. Or he's gonna lock the door and not let me in. Or he will spend 2 years reviewing my design and then not getting back to me. Or if I do buy him lunch, then he's like, well, how do you expect me to hold that weird organic looking thing? Like, how am I going to hold it in the machine and then come in and machine it and know that it's going to stay there and not wobble around?
Fixturing.
Yeah, so the fixturing can be a little bit of a nightmare. So like one good example of that is like this is a turbo pump here on the right-hand side. It's composed of several components, but like the turbo pump is essentially like the heart of the rocket. It like pumps the fuel through the rocket and gets it to where it needs to be.
This is beautiful, though.
I know. I think it's like 8 different components for this particular one, and we did this in a collaboration with I think Colorado State. But you can see that the holes and the channels and everything like that is like very like organic looking. They're not like square. They're not diamond. They have like almost a teardrop shape to them. Slanted,
There's a
beautiful
real
shapes.
aesthetic.
There is a
here,
real
actually.
aesthetic.
But again, it's not just, this isn't just form, it's form and function. Because art does not have to be pure form. It absolutely can be form with function. And it feels like that's exactly what this is.
That's exactly what this is art. This is the art that I make every day. I do consider myself a little bit of an artist because I don't like to be constrained to the conventional squares and rectangles and things that traditional manufacturing is used to and is comfortable with. And I'm like, no, we need to get uncomfortable. It can also be beautiful. Like, why can't it not be beautiful when I create it?
We like the multi-hyphenate here, so you know this is allowed. You're welcome in the multi-hyphenate space. I think this is good. Do we have time to ask any questions? Yeah, I was gonna say
One or two quick ones.
I did want to put it out there because I do feel like this is weird stuff, and there might be some questions. If there's not, then that's fine too. But it does look like there is. I was gonna say all the way in the. I was gonna say, we have 2 people who are asking questions, and they're right front to back. I was gonna say the back, and then the one in front, I suppose. Yes, you sir, please. 3D EO.
Yes, that is hybrid manufacturing. I think that's amazing, but I've only seen it thus far on like smaller components, and then it's amazing if you get it into repair. When I worked at Siemens Energy, we had like a lot of blades and vanes, and so the blades are inside of the engine and they're spinning at thousands of RPM really, really quickly, and it's really, really hot. And obviously the blades will wear on the tips, and then we have to come out and then repair them, or like we have to bring them in for repair. And sometimes you can't repair them because they're so thin and so small, but using a process like that, now we can. So now this like device that we spent like, I don't know, thousands of dollars making, we don't have to throw it away. We can just repair the tip and then keep it in service life for like dozens more years.
That's cool. That's very cool. I was gonna say you had a question as well.
I know that this is used to make like very complex fluid bodies and so on. But then you can have parts where they would need supports. How well do
Supports.
So that's a physics problem. And also that's where the art comes in. That's where my artistry truly shines, is like, how do I support certain types of geometries or certain types of shapes? And then you have to blend that art with physics. So I just call it physics-based art. But essentially that's how it works. And in terms of like supports, like what you would use in like commercial stuff, the tree supports, like the super cool Prusa, like the ones that look like fingers that crawl out.
We love a tree support.
Yeah, we can't do those. The little tips will break off due to the stress from the metal printing process. But like block supports, the infill supports that I see you all use, we can also use those. It just depends on the metal. Some metals will not at all take anything but solid material support. So like Inconel.
You're just grinding that off.
Yeah,
after.
you're just gonna have to like grind that off. But aluminum,
Yikes.
you can get away with. Titanium sometimes. Sometimes titanium's in a good mood.
Say we've got someone who's been very, very patiently holding their hand up for a while. Yes, you, yes, you.
As far as metal printing, do you prefer like binder jet and then anneal, or do you prefer like direct sintering?
I work in laser powder bed fusion. I do like binder jetting, but you can't really print anything bigger than a baseball successfully, because like to do the binder jetting process, like it works great for anything smaller than a baseball or fist size. Anything bigger than that, and like in the green state, you risk it crumbling apart, and then like the R&D on it is just like intense. But I do think that like for thousands of parts, yes.
We got here.
Looking at the image up there, I see the holes going in, and I assume that they don't just go straight in. They probably have some sort of curving path. How would they machine that to get it to the
So you would not be able to machine that. You would have to do some testing on like how the surface roughness impacts the way the fuel is flowing. And then if it's still not good enough, then you can do like a chemical polishing. That one's really cool because then you put like a little like acid solution in there, and you pump it through really quick, and then try and suck it out fast so that you don't take off too much material.
Fun.
Yeah, so much fun.
Doesn't sound dangerous at all.
Yeah, also, you know, if you leave it on there just like a second too long, then you have to redo the whole part.
Yay! What we got up here?
In your mind, what does the future of laser powder bed fusion for metals really look like? Oh my God! Like, do you see it becoming like multi-beam machines and growing to higher throughputs, or do you see finer resolution, more materials? What excites you?
So what excites me the most is that, I guess we'll end on this one. Supply chain impacts. So when I worked at Siemens, I worked on a project called Inventory, and we essentially went through our entire product line. I mean, we did own NX, so it makes it a little bit easier. But we went through the entire product line, and we found everything that would fit within the bounding boxes of a metal 3D printer that was made out of metals that were like, you know, that would work with the metal 3D printers that we had. And then we started making digital twins. And so if like a power plant were to go down in India, we would have metal 3D printers stationed throughout like a global network, and we could 3D print at the nearest like printer, and then we would print the part, have it qualified, we'd have the digital twin fully done, then we would ship the part directly there, and we wouldn't have to pay for warehousing, we wouldn't have to pay for shipping, it would cut down on like global costs. It was like a really big green initiative that they were pushing, and it was a really beautiful dream. I don't know where it's at currently because I'm no longer there, but that is what excites me the most. It's like global supply chain impacts. Like if we didn't have to wait forever for parts, for things to be repaired, if we could just print it at the closest location that we need it. Like that would have been like super important for certain global events that are happening where it's like, oh, this guy is bullying this little guy. Maybe we might want to like send them some spare parts. You can fill in the blanks
Very
there.
diplomatic of you.
Thank you.
But that is probably a good thing to end on. So I do apologize for everyone else, but we have to let other people come on the stage. But thank you so much for joining us all today. Thank you so much for, like, please give SJ a round of applause for coming and sharing their knowledge.